class you have already done the relation R on a set A to itself. Let R is a relation such that A to A, that means if A and B are any two elements in the given set A, then A is related to A, or R is the set AB, set of ordered pairs AB, such that A and B belong to the given set A. So that is how you define a relation R from set A to itself, that is on a set A. Now today we have to mainly do the types of relations. What are the different types of relations? So you have three types of relations. Number one, reflexive. Number two, symmetric. Number three, transitive. I'll define all the three one by one. So number one, reflexive. Given is a relation R from set A to itself is said to be reflexive if for all A, let A is any element, in the given set, small a is any element in the given set A, such that A is related to A, or AA belong to R for all A lying in the given set. Then the relation is said to be reflexive. For example, if I choose the set as set of natural numbers and the relation is equal to, that is, the relation is equal to on the set of natural numbers, we want to check whether it is reflexive or not. So let A is any natural number. So safely I can say A is equal to, for example, if I choose a particular natural number 5, 5 is equal to 5, 6 is equal to 6. So that means A is equal to A for all A lying in set of natural numbers. So we can conclude that the given relation equal to is reflexive on the given set of natural number n. Now second type is symmetric. Let A and B are any two elements of a given set A, such that A is related to B. If it implies that B is related to A, or in other words, I can say AB belong to R implies BA also belong to R for all AB, for all A and B lying in the given set A, we say that the given relation R is symmetric on the given set A. So a relation R on a given set A is said to be symmetric provided A related to B implies B related to A. Let's take a simple example from geometry. Given is a set, say denoted by capital L, the set of lines in a plane. Let L denote the set of lines in a plane. And the relation R I am taking as is perpendicular to. R is a relation is perpendicular to. So let us check if this relation is perpendicular to on set of lines is symmetric or not. Let L1 and L2 are any two lines in set of lines L such that L1 is perpendicular to L2, or I should start with such that L1 is related to L2. If L1 is related to L2, that means L1 is perpendicular to L2. And you know, geometrically, that if L1 and L2 are two lines, such that L1 is perpendicular to L2, then obviously it implies L2 is perpendicular to L1, or L2 is related to L1. Or in other words, L1 related to L2 clearly implies L2 related to L1. So we can conclude that the given relation R, that is perpendicular to relation, is symmetric on set of lines in a given plane. So that is about symmetric relation. Now the third is number 3, transitive relation. When a relation is said to be transitive, a relation R is said to be transitive on a given set A. Now let A, B, C are any three elements in a given set A such that A is related to B and B is related to C, implies A is related to C. Or the same thing can be expressed as AB belong to R and BC belong to R, implies that AC belong to R. Then the relation is said to be transitive on R. Let me take an example. Transitive on the relation R is said to be transitive on the given set A. Now let me take an example for this. Let the relation is defined as is greater than relation on set, say the set is set of natural numbers n. We want to verify that the relation is greater than is transitive on set of natural numbers. So let A, B, C are any three natural numbers. I'll take numerical values also. Let us first try. A is related to B and B is related to C. A is related to B means A is greater than B. B greater than C, B is related to C means B is greater than C. So you know clearly if A, B, C are three natural numbers such that A is greater than B and B is greater than C, then obviously A is greater than C. Or in other words, A is related to C and hence the given relation R is transitive on set of natural numbers. Let me take a numerical example. For example, say 7 is greater than 3 and 3 is greater than 1. Obviously 7 is greater than 1. So the relation is greater than is transitive on set of natural numbers. Now you have seen that equal to relation on set of natural numbers is reflexive. It can easily be seen that it is symmetric as well as transitive. But for all the relation, like for example perpendicular to, you have seen perpendicular to relation is symmetric, but you can check yourself that it is not transitive and it is also not reflexive. So now I give a fourth type of relation, a fourth definition, that when a relation is said to be an equivalence relation. Equivalence relation. What do you mean by equivalence relation? A relation R on a set A to itself is said to be an equivalence relation if it satisfies all the three properties. All the three properties. What do I mean by properties? That is reflexive, it is symmetric, number 2, and as well as it is transitive. So if a relation on a set A is reflexive, symmetric and transitive, satisfy all the three types, then is said to be an equivalence relation. So you can check the earlier three examples which I have taken one by one, equal to on set of natural numbers, then is greater than on set of natural numbers, perpendicular to in set of lines in plane, that whether they are reflexive, symmetric or transitive. That means the three relations separately, which one of them is an equivalence relation and which one is not and why. Now let me take an example. Just note down an example. Show that the relation R, in set Z of integers. You know here Z denotes set of integers. So in set Z of integers given by, the relation is defined as, given by R is defined as set of ordered pairs A, B such that 2 divides A minus B, or A minus B is divisible by 2, or 2, it may also be said as 2 is a factor of, A minus B, then we say A is related to B. So what is the question? I repeat, show that the relation R in set Z of integers given by R equal to AB such that 2 divides A minus B, we have to show is an equivalence relation. That's what we have to prove. Take proof. So to prove that this relation is equivalence, what is required? We need to prove it is reflexive, symmetric, as well as transitive. So let me take one by one. Now for reflexive, let A is any integer, A belong to Z. Then what do you say about A minus A? A minus A is 0. So that means A and A minus A is 0, which is very much divisible by 2. So A minus A is divisible by 2. So we can conclude that A is related to itself. Every integer is related to itself. So we conclude that the given relation R is reflexive on set of integer Z. Number 2, let us check symmetric. Let A and B are any two integers, A, B belong to Z, such that A is related to B. If A is related to B, that means A minus B is divisible by 2. Now you know A minus B may be rewritten as, take minus common, minus times B minus A. So A minus B is divisible by 2, or in other words, minus times B minus A is divisible by 2. And if minus times B minus A is divisible by 2, so should be B minus A, that is B minus A is divisible by 2. Let me take an example. For example, if 4 is divisible by 2, then minus 4 is also divisible by 2. Or if minus 4 is divisible by 2, we can say 4 is also divisible by 2. So B minus A is divisible by 2. So what do you conclude? That B is related to A. So finally we find that A related to B implies B related to A. So we can conclude that the given relation R is symmetric relation. Now third, transitive. Let A, B, C are any three integers such that A is related to B and B is related to C. If A is related to B, what does this imply? That A minus B is divisible by 2, and B is related to C implies B minus C is also divisible by 2. And you know, that if two numbers are separately divisible by 2, so should be their sum. So and hence a minus b plus b minus c is divisible by 2. Here a minus b plus b minus 2, b will be cancelled. So we may conclude that a minus c is divisible by 2, or in other words, a is related to c. So what do you find? How do you conclude finally that a related to b and b related to c implies a is also related to c, and hence the given relation R is transitive on the set Z. So here we find that the given relation R is reflexive, is symmetric, and transitive. Satisfy all the three, so we can conclude that the given relation R is an equivalence relation on the given set of integers Z.